Hello, this is Daniel, and today we'll discuss the final topic of our machine learning tutorial, which is gradient descent. Gradient descent is not a machine learning algorithm, but an algorithm to solve the cost functions in linear regression and support vector machines. The presentation slides and source codes I use here were obtained from the Intel machine learning course. I reorganized the contents for easy understanding. You can download the original content from the website using the link. Then let's get started. By now you know the basics about linear regression. If you don't, please watch my previous video for it. Regression tries to find the best line to input data. Here beta 0 is the intercept and beta 1 is the slope of the line. Finding the best beta 0 and beta 1 in the cost function j gives a minimum error between y observation and predicted y. This process is called an optimization problem. Suppose a quadratic function is given. The x-axis represents beta values, and the y-axis represents the cost function j of beta. This function is minimal at a specific beta value, the optimal point, beta optimal. We want to find the beta value for which j function is minimum. Gradient descent starts with an arbitrary beta value on the function, say beta 0 on the blue point on the curve. Our goal is to approach the beta optimal, which is the function's minimum. In which direction should we proceed to a smaller value on the function, left or right? In visual inspection, it is evident that we have to move in the left direction of beta 0. The idea is to calculate the slope or gradient at beta 0 and subtract it from beta 0. Then the next beta value, say beta 1, is found at the left of beta 0 since we subtracted the positive slope from beta 0 value. We will be iterating step by step to reach the beta optimal. This idea can be generalized to complex cost functions in real-life problems. Let's consider linear regression, where the cost function has two parameters, beta 0 and beta 1. Then, we have a three-dimensional surface representing the cost function of beta 0 and beta 1. From the arbitrary starting point x on the surface, we have many choices for the next move. The term gradient is analogous to a derivative or slope in higher dimensions. We compute the gradient, indicating the direction of the largest increase. Then the negative gradient represents the largest decrease at the point. So, moving towards a negative gradient can reach a lower surface position. The gradient of the j function is a two-dimensional vector. Each vector element represents the partial derivative of beta 0 and beta 1 respectively. Once we start at w0, we compute the gradient at w0 and subtract it from the original point. Then we can obtain the next point w1 in the direction of moving lower. We can see in the formula that there is another constant parameter, alpha. The alpha in gradient descent is called step size or learning rate. It determines how fast we move in the direction. If alpha is large, we take a big step and the next point w1 will be a much lower value. Thus, it is quickly descending. Conversely, if the step size, alpha, is small, reaching the minima will take much time. It descends slowly. Now that we are at w1, we recompute the gradient to find out the steepest slope or direction at the point w1. By applying the same formula, we move to w2, descending along the surface. The next point, w3, is calculated in the same way. After many iterations, the gradient will be 0. At that point, we converged at the minimum. So far, we've learned the mathematics of gradient descent and how it works. Let's move on to the efficiency issue. Theoretically, we have to compute the formula for all the observed input data. But calculating the gradients in higher dimensions, especially for large-scale data, takes too much time. Modifying the formula allows us to obtain efficiency instead of losing mathematical rigor. It is the stochastic gradient descent method. We use a single data point to compute the gradient instead of all the input data. The formula removed the sigma term, calculating the sum of gradients of all data. Taking the gradient of just one point may not guarantee the best moving directions, but in practice it is good enough and costs less for large-scale data. With sufficient iterations, it also converges to a reasonable minimum. That is all I prepared. Thank you for listening, and this is the end of our machine learning tutorial series. Thank you for following along this tutorial series with me, and see you in the next video. Bye!